Welcome to our talk on PG Keys, Keys for Property Graphs. This is work of the Property Graph Schema Working Group of the Linked Data Benchmark Council. Members of the PG Keys team range across industry, academia, the ISO standards community, as well as the broader Linked Data Benchmark Council. The council itself consists of industry and academic partners coming together to share expertise and experiences and discuss and form consensus around graph data management technologies. In this talk, I'd like to briefly introduce PG Keys by unfolding the title of the paper. So first, why PG Keys? The first part of this question is why property graphs themselves? Graph structured data and graph analytics are increasingly ubiquitous in a wide range of contemporary practical applications. Typically in situations where the interest is on modeling entities and their relationships. Some examples include, say, role analytics in social networks, pattern discovery in bio and chemical information networks, routing problems in logistics and transportation in smart cities, analytics on communication networks, financial networks, crime networks, and knowledge management in the form of knowledge graphs. In this space, the property graph model is an upcoming standard being used already in a wide variety of technologies where, in a nutshell, the data consists of node and edge labeled directed graphs where node and edge objects have properties, that is, attribute value pairs, local data. As a small example here on the right, we see a property graph consisting of 6 node objects and 6 edge objects. So as an example, we have node P2, which is labeled as person. It has 2 properties, name and login, with value Akira and Akira. We have another node, F0, labeled forum, which has a single property, title, with value databases. And there's an edge labeled join from Akira to this database forum with its own local property year with value 2019. Is the second part of PG Keys, why keys for property graphs? Well, if we think back on the history of and success of data management solutions, keys are, well, key in data management for identifying, referencing, and constraining objects in a database. So for example, if we consider person nodes, we can have keys constraints such as people are uniquely identified by their login ID. Person nodes can be referenced using one of their email addresses, and we could have that, it's mandatory that each person has at least one email, and of which at most one can be the preferred email. We could also have that person nodes have 0 or more aliases, which are exclusive to the person. That is, no 2 people can share an alias. Furthermore, in our example, we could have that, say, discussion forum nodes are identified by the forum's name and the person who moderates the forum. So using some graph ASCII art here, we could have in the structure of a node labeled person with an incoming edge labeled has moderator from forum. This forum is identified by its name and this person, this moderator. Well, keys are vital for managing both identity and integrity in the graph. So for example, in an integrated knowledge graph, modeling key constraints in the underlying data sources and in maintaining data quality and consistency in the graph itself can be vital for the success of the application. And why keys and why now for property graphs? Well, because property graph technologies are being standardized now in ISO. And furthermore, system vendors are moving ahead in diverse ways in reasoning about and supporting key-like constraints. The LDBC and Property Graph Schema Working Group is a community of researchers, practitioners, and database vendors working towards consensus recommendations informing the standardization process, which is ongoing now. If we look at the current support for keys in graph databases, it's very limited and diverse. Indeed, if we look at the landscape, we have that some systems offer property-based primary keys but just for nodes. Some systems support uniqueness constraints, and some systems support mandatoriness. Yet, if we look at contemporary applications of graph data management, We need to support all of these and more to satisfy these needs. And if we look in current tools, we have that there's already a significant drift between database vendors. We need to get on the same page, and we need to bring the best of decades of academic work to the needs of industry and practitioners. So in the rest of this talk, I'd like to give a brief guided tour of our proposal. Of course, full details can be found in the paper. Okay, so in a nutshell, PG keys are patterns of the form for some object identified by a query pattern. Here in red, say the key scope, we will have that some objects described in a descriptor, so key values, identify this object here in green. And looking at and discussing the use cases arising in practice, we distilled out 4 design requirements which guided our construction of PG keys. The first is that we should have a flexible choice of key scope and descriptor, the descriptor of key values. Secondly, we should be able to support a definition of keys for nodes, edges, and properties. Thirdly, we should be able to identify, reference, and constrain objects. And finally, the formalism should be practical. It should be easy to validate keys. So let's take a look at how we've satisfied each of these 4 design requirements in turn. So concerning flexible choice of scope and key values, we have that we declaratively specify the scope of the key and its values, and you can do this in your favorite property graph query language. This is a parameter of PG keys. Here in the talk and in the paper, we use a cipher-like syntax, which is a popular, well-known property graph query language. So for example, we have, suppose that we want that each person in our person forum graph is identified by their login. So as a PG key, we would specify this as for P within this pattern, and this pattern is just a query which selects all nodes P bearing the label person. So for all such objects P, we will have that they are identified by their login attribute value, p.login, here in green. Suppose next that we also want to constrain that each forum with a member is identified by its name and operator. So here our scope is defined by a slightly richer query pattern, those fora F with an incoming edge labeled join from a node labeled person. So for all such nodes F, we will have that they are identified by the name value, so the value that F takes on its name property, and the identity of the object P within the value descriptor here. So we have those P that are nodes labeled person having an outgoing edge labeled moderates to this forum F. Concerning the second design criteria, we'll illustrate how to specify key constraints on nodes and edges. Right, so for example, as an example of a key constraint on node objects, we had that each person node is identified by the value of their property login. And as an example of an edge, a key defined on an edge, suppose that we want that each joined edge, so each edge object with the label joined, is identified by its endpoints, right? In other words, no other joined edge has the same endpoints, so one cannot join the same form twice, right? So here we're looking for those edges E, labeled join, from a node labeled person to a node labeled forum, and this edge is identified by the identity of the person node, a combination of the person node and the forum node. Concerning our third design constraint or criteria, we have that identification of objects is provided by the identifier Q phrase, right? So here an example of for those for F, that have a member, right? So that have an incoming edge labeled join from a node labeled person. We have that such nodes F are identified by their name and the person who moderates the forum, right? So those nodes P that have labeled person and outgoing edge labeled moderates to this forum F. Here, identifier is actually a shorthand for three constraints. First, this is exclusive, so no objects in the scope share a key value. It's mandatory, so each object in the scope has at least one key value. And finally, this is a singleton, so each object in the scope has at most one key value. So this is a shorthand. This is what we mean by name and the person, the ID of the person node being an identifier for such fora. So thinking in terms of what we're familiar with in SQL, exclusive corresponds to unique, mandatory corresponds to not null, and singleton, well, it's always ensured by a first normal form. Right? In property graphs, all three of these features are needed. Okay, so looking at relaxing identifier key constraints, we have that referencing is provided by just the combination of exclusivity and mandatoriness, right? So we could have a key on nodes stating that emails aren't shared and each person has an email. So this is for those P that are nodes labeled person, we have that the email associated with this node P via a has edge is mandatory and it's exclusive to each person. And constraining can be done in many ways, right? So for example, we could say that for people nodes, their aliases are exclusive, or that for people nodes, the preferred email, right? So an email object associated with a person via a preferred edge is exclusive, and there's at most one. Okay, and finally, our fourth design criteria is validation, ease of validation. And it's, as we discussed in the paper, to check that a PG key holds, we can run queries to find violations. Right? So it amounts to a query evaluation using, so for example, your favorite underlying query engine. So for instance, suppose we wanted to validate the key constraint on people node stating that emails are mandatory and exclusive to a person. Well, this PG key constraint on person nodes holds if both of the queries below return nothing, right? So that is, we're looking for two different people having the same email, right? So if we do find two such people, there's a violation of this key constraint. And we also would look for matches of person nodes that don't have an email, right? So this would violate the mandatoriness of having an email, right? And incremental validation or batching will require additional mechanisms, but simple validation of PG key constraints on the current instance amounts to running queries. Okay, so that's the basis of PG keys and the design criteria that we set for ourselves based upon our analysis of the needs of contemporary graph data management. We also consider in the paper several natural practical extensions to the PG keys formalism. So the first is null values, right? So if your data can have null values, then we need to know what references to, say, in this case, property values mean if they can take on null values, right? So for example, if we're looking for people, nodes labeled person, and we want to filter only those people where the age is above 30, what this will mean if age can take on a null value. So in our approach, we design PG keys such that one can validate a key K by executing a query, an appropriately written query that finds violations of the key K. So as you'll find the details in the paper, we thought everything through again to see to which extent this goal can be reached. And essentially, we need to enforce in this case, that p.age is greater than 30 and p.age is not null. Again, more details can be found in the paper. Another practical extension is to have support for regular path queries, right? So for example, as an example of a regular path query, in a key constraint, suppose that posts and forms can reply to other posts, and we want to ensure that each post is identified by its reply to path in the form where it was posted. Then in the descriptor of the values, then we would have then a reply to, but now 0 or more times. So a path of length 0 or longer using just reply to edges. Right. And then finally, our data model already allows complex values such as tuples, sets, lists, JSON structures. So in order to use these in PGKeys, we'd have to leverage the query language, right? So we need to use the parameter, the query language used to instantiate our formalism to access and reason about the complex values, right? And so suppose that we have that each person has an official telephone number and no two persons have the same official telephone number. Well, then we can do this by inspecting the phone collection and looking at official phone numbers within that collection. Okay, so that concludes the kind of overview of the results that are presented in our paper. Now looking ahead, so PGKeys is already informing the design of ISO's new GQL query language via the LDBC liaison with ISO. And more broadly, PGKeys is a call to action to industry and academia to guide the design and engineering of commercial and non-commercial graph systems and solutions, and for the academic study of the wide range of open problems that remain to be studied, including, say, validation and maintenance of complexity for specific query languages, studying implication and inference problems, static analysis for optimization purposes, the study of richer constraints for property graphs. And the property graph schema working group is just getting started. So we're really right in the thick of the design of a schema language itself and other constraint languages and extensions to the property graph model itself driven by practical applications. So for example, meta properties. So thank you very much.